Thank you very much. Hello everyone, I am Mihir Dharmadhikari. I am a PhD student at the Autonomous Robots Lab at Norwegian University of Science and Technology. What I'm talking about today is the work done by Team Cerberus in the DARPA Subterranean Challenge, and I'll be mainly focusing on the exploration autonomy in the underground environments. So first, I would like to give an overview of what the Subti challenge was. What you see over here is the robots of our team exploring in the underground environment built for the DARPA Subterranean Challenge final event, which was the finale of this 4-year long competition. What you see here is all the robots exploring in these different types of environments. The way this competition was structured was that the robots had to go inside these underground environments and autonomously operate and detect certain objects of interest, which we call artifacts, and localize them within 5 meters of errors from the ground truth. And that's how you get points. And I'm proud to say that Team Cerberus was able to get the first position in this final event. I also would like to credit Team Cyro Data 61, who got the same score as us, but the tiebreaker was in our favor. So first, let's look at how these environments look like, what are the challenges, so that we can understand the methods in in a better way. So you can see that these environments are very diverse. You can have the settings from underground mines, human-made environments like subway stations, natural caves, and even within these, there are a lot of different varieties, lot of different terrains, lot of different geometries that all these robots need to tackle. What you see here is a fly through of the environment that was built for the final event of this challenge. As you can see, it consisted of 3 different types: the tunnel, urban, and cave. All of these in one single course. So the robot had to tackle all the different challenges that were posed by all these different types of environments. So a little bit about our team. Our team Cerberus is a collaboration between different universities, research labs like ETH Zurich, NTNU, University of Nevada, Reno, UC Berkeley, Oxford, as well as some companies like Flyability and SNC. We took the approach of having a system of systems consisting of primarily aerial and legged robots that can overcome each other's limitation and work together to solve this problem. Oops, sorry. How do I? Okay, thanks. So to work in these environments, the different sub-modules that need to work together are shown here. The research of Cerberus primarily focused on the core modules, which involve building the robots and their mobility, resilient perception, and resilient autonomy. But to support them, you also need good communication deployed in this environments and things like object detection for actually getting the points. So I'll first start with the most important part, the robots themselves. As I said, we primarily had legged and aerial robots that you can see here. And we also had a wheeled robot for mainly used for communication extension in these environments. It had a tethered optical fiber and a high gain antenna to extend the communication. Now, why we have this collaboration of legged and aerial? So if you see our legged robot, it is an Animal C robot that we use in the final event. It has a VLP-16 LiDAR, 2 more dome LiDARs from Beeple, an AlphaSense camera, which has 5 different cameras, color and mono. And on the top is a pan tilt head, which has a zoom camera and a thermal camera. So in general, a huge sensing payload capacity that can give a rich amount of information, as well as being a legged robot, it can traverse for a long time and different types of terrains. But it is slow and it cannot access certain areas. And that can be complemented by aerial robots. So even though they have limited payload capacity, they can go faster and in a lot of different areas. So you see here in the middle a traditional quadrotor platform, as well as a collision tolerant aerial robot that we built to navigate in very confined, cluttered environments. The second part, or the second module, is perception. We developed both resilient single robot perception and a centralized mapping system for merging the maps of all the different robots in the environment. To for us, this such a system to operate, we should first look at what are the main challenges. So these environments are usually GPS, or actually always GPS denied. They can be completely dark, filled with obscurants, can possess geometric self-similarity, maybe textureless, and they usually are kilometers in scale. And these are the challenges that we need to address. For that, to build a resilient perception system for a single robot, we took a course to fine approach, and the method that we developed, we call it ComSlam, complementary multimodal SLAM, which combines different sensing modalities like LiDAR, vision, thermal vision, IMU in a coarse to fine hierarchical fashion. The reason for doing this multimodal approach is different sensors respond to different sensor degradations in a different way. And each of these modalities can get degenerate. So we explicitly... Okay. Ah. So each of these sensing modalities can get degenerate in different conditions, but we explicitly detect which modality is getting degenerate and pass through the solution odometry from the other modality to still continue operating despite having degeneracies in certain modalities. So this is just a small video of showing the importance of this. On the top, you can see a purely LiDAR-based method. The robot here is going in a self-similar tunnel, so the LiDAR is degenerate, and the pure LiDAR-based method cannot handle it. But at the bottom, oh, is the video paused?
The proposed approach is able to correctly estimate the robot pose and produce a realistic map of the self-similar
Anyway,
environment.
so at the bottom, what you can see is because we detect this degeneracy explicitly,
In our
we can
proposed
remove the LiDAR modality and pass through the vision and still continue accurate localization.
process.
Finally, the third module is autonomy. The autonomy of Cerberus aims to is built on the characteristics of the sub-T environments, which are long, large-scale, multi-branch, multi-level, having difficult terrain. And then we also want this autonomy solution to have minimal human input so that the robot can work outside communication range. And finally, since we had a heterogeneous team of different types of robots, we want a higher level exploration strategy to generalize across them, but still account for all the traversability and robot specific constraints. So to that end, we built this method called graph-based exploration planner, which operates in a bifurcated manner of planning efficient paths locally, but also keeping a track of unexplored areas in a lightweight graph across the whole map, and reposition the robot as the local exploration fails. What you see here is one of our robots exploring in an underground mine before the actual final event. You can see the robot being able to tackle different terrains, multi-branched environments, and later also doing repositioning. I won't go through the whole video due to time constraints. And another mission with an aerial robot in a different mine. On the left, you can see the graph and the paths that the robot is taking. And on the bottom, you can see the map as the robot builds. I would like to highlight that everything that runs on board the robot, and the human is not giving any low-level commands other than starting the mission and stopping the mission. A key lesson that we learned is field testing is extremely important. So we tested in a diverse set of environments, all that you can see here. And this is the final result from the final event of the sub-T challenge, where you see the maps and the paths of all the robots. This is the same. I'll just skip this. And finally, I would like to thank all the team members of Team Cerberus who helped this whole thing happen. We release a lot of our code as open source, so do check out on the on the GitHubs of all the different labs. And that's it from my side. Last note, we are hiring 10 PhD and postdoc positions. So if you are interested in and find what I presented cool, feel free to contact us. Thank you so much.
So is there any question you would like to ask?
Maybe I just.
Yeah, you can just, that.
Okay, thanks. Live listening from the German Research Center for Artificial Intelligence. Thank you very much for your really nice talk.
Thank you.
Very interested in the global fusion of the global map.
Okay.
I don't know if I really got it, but are you fusing more on a higher level, or are you really fusing all graph nodes in one consistent global map, or and how maybe you can think a little bit how you do this?
So we do fuse in one consistent global map. But the way this is built is it's called M3RM, where we take the point clouds and the visual features from different robots. And as each of these robots maintain a post graph on their own, they send a lightweight version of that, which is then combined on a central system. And this combined post graph is optimized to get the refined map of all the robots.
Maybe you would like a loop closure having the relaxation of the whole graph.
Yes, so loop closures are also incorporated in this. Yes.
How did you decide which team member did which job?
So it was a lot based on which lab has expertise and background in what field. For example, the robotic systems lab has experience in legged robots. So they were primarily responsible for the mobility development of the robot and low-level navigation.
Oh, I mean, so did all robots start at
Okay, you mean robot-wise? Sorry. Yes. So all the robots had to start at the same point. And then we did not have the robots did not decide themselves which areas to explore, but the human gave them higher level bounds. So this robot explores this bound, the robot explores this bound, and then the robots undertook the exploration and navigation on their own within those bounds. Yes.
Maybe a question related to the question. So you have a centralized, just to understand.
Yes.
You have a centralized unit which computes the global map and then distributes to all the team members.
So the global map is not actually sent back to the robots. This global map was primarily used to refine the positions of the artifacts that were detected. So since the individual robot odometry might drift, the location of the detected object might also drift with it. But if we can correct it globally, then the reported location will be better. So it will be possible on the central map, but it will not be sent back to the robot. Thank you.
Thank you very much.